that we did was so we have seen that for flow over cylinder and flow past a sphere, how we can estimate the average Nusselt number, and from there, how we can calculate from the correlations, how do we estimate this average H value of the heat transfer coefficient. So this was for a single cylinder exposed to a flow, and this was for a single sphere. So which means now if we look at the expression once again, so typically what happens that this, if we try to write about this Nusselt number of a cylinder, what we can typically write is that HD by K. I hope I'm audible, guys, right?
Yes, sir, you're audible.
Okay, fine. Okay. So yeah, so Nusselt number for a flow over a cylinder, it is HD by K. Again, this is the average Nusselt number, which typically we can write C is a constant, Reynolds number to the power m, and Prandtl number to the power n in generic form. So this is the average Nusselt number that we can write for flow across a cylinder. And we can write this in this kind of a compact form. We have seen the elaborated expression, which are more accurate, but also such kind of expressions are useful in order to have an estimate. Okay, so where n is always 1/3. Okay, and this constant C is experimentally determined, and the value of m, okay, this value of m is given in this kind of a form or table. Say, if you look at this table is available in Encyclopedia Holman, wherever the textbook that you can find. So what happens here, that if a cylinder cross section, if a cylindrical tube is there, that means the cross section is a circle, whether that is the fluid that is flowing over it is a gas or liquid, and depending on the Reynolds number range. Okay, now how do we calculate Reynolds number? What would be the characteristic dimension for calculating dV rho by mu? Because we need d, so that is the d for a cylinder, that is the diameter of it. So from there we calculate the Reynolds number. We look at appropriate where this Reynolds number is, whether in which range it is, and accordingly we use any of these expressions. Now, if I show it in a zoom view, you can see that the Nusselt number now is having the value of C is different for different Reynolds number, and the value of m, the Re to the power m that we mentioned in this expression, in the compact expression, the m value is changing, and the n, the Prandtl number to the power 1/3. The reason we gave in the previous classes that it is the best fit that happens, that analytically derived expression, that it has been shown that at Prandtl number to the power 1/3 during the boundary layer derivations, we have seen that. So that 1/3 remains same here. Okay, and these coefficients changes, or they say the prefactor actually changes, and the indices changes for the Reynolds number. So similarly, if that cylinder has a square cross section, okay, then if that is a gas and the Reynolds number is flowing like this, then we have a different correlation. So similarly, depending on the different arrangement of the cylinder and its cross section, And here, this is the vertical plate. This is the ellipsoid kind of a body. Depending on the Reynolds number, there are correlations available, which we have to use when we are given a problem. But again, typically these are not meant for memorizing. Okay, so either say we explicitly give this expression whenever required, but the point is that for a couple of the things, okay, particularly for the cylinder, these expressions, any of it is useful for you to remember that what is the typical range, say 0.3 to 0.8 is the range that M value varies for this case. So the point is that all the relations and all these correlations that are shown here is basically derived for a single cylinder or a single object. Now, say consider there are situations, and also particularly if I forgot to mention, that is for the smooth surfaces. So we have smooth surface, the external surface is smooth, okay, and a single object. Flow is happening over in that scenario. So that means if there is surface roughness is there, okay, and say due to this presence of the surface roughness, there will be local turbulence or say the onset of turbulence. Then it actually affects the drag, and consequently it affects the heat transfer coefficient. Okay. Now the point is that these relations, now you shouldn't be confused that okay, you mentioned last time that this is the relation for a cylinder. Okay, but provided this is the range where we are applying. Okay, the Churchill-Bernstein relation. Now again, you are mentioning here these are different relations. Now which one I should use? Ideally, you should use this elaborate expression, which is more accurate. This one is more accurate. Okay, so if you can use this one, you would get more accurate result. But to have an estimate, say we are the engineers, we typically want to have a quick number to understand that how much we need. So in order to estimate that number, this kind of relations actually give us some guess or some range or estimate that what would be that number, that heat transfer coefficient, or so the based on these calculations, if we calculate the net rate of heat transfer, we can estimate that what is the heat exchange or amount of heat exchange that is happening. So whenever possible, you use those previous equations that I showed last time for the cylinder as well as the spherical object, and these are the relations in order to have a near close enough estimate to those expressions. Fine. So before I go into the deviations from here, because today we will learn that if now there are multiple such objects that are aligned to the flow, okay, so what will happen in those cases? Because one thing you can understand that when there is a flow through a pipe, inside a pipe, okay, and flow through multiple such pipes, whatever we calculate for a single pipe, if we multiply that by number of these pipes that are happening, that we get the result. But when there is an external flow, okay, and the flow is happening over it or across it, then the presence of other object, okay, is not accounted by this simple manner, or it will not happen in that way. So what will be that case? That means we can say that there is a bank of tubes that are placed in a systematic manner, say, okay, and then the flow is happening across it. What will be, or how can we estimate the heat transfer coefficient in those cases? So today we will see that. But before we do that, let's apply whatever the understanding we have, okay, for a simple problem. In fact, two problems we will do, one for the spherical object and one for the cylindrical object. So say the problem says we have say a rod. Okay, so say we have a 10 centimeter diameter rod. This is of 10 centimeter. Okay. Then we have its external surface temperature of say 110 degree. That we can say is TS, surface of this pipe or rod, whatever you can think of. Okay. Now this area across which the flow is happening, is not say insulated or protected against any of this heat transfer. We have to calculate what is the say rate of heat loss per unit length of this rod when this air that we have here is at 1 atmosphere. Okay, the approach velocity that is coming at 8 meters per second, and the ambient temperature is 10 degrees centigrade. So these information are given. That means this wind is at 8 meters per second speed. We have 10 degrees centigrade of the outside temperature. Okay, and the surface temperature of the rod is 110 degrees centigrade. So what is the rate of heat loss from this object? Okay, and yeah, that is it. That is it. So what is, you tell me what is the rate of heat loss, and for that what you need, what information you need. I will tell you those information in order to solve this problem. Consider, although you have not read radiation in detail, but consider radiation is negligible and air is ideal gas. So what are the information that are necessary to solve this problem? This is the first step.
Molecular mass of gas.
Molecular mass of gas. And why do you need that?
To calculate density.
Density. Okay. And so you need, say, density of
viscosity.
Viscosity of air. Okay. Any other thing?
K.
K of the material, right?
Yes, sir.
Okay. And is there anything else? But you are not mentioning at which temperature you need those values, because for air, for the gaseous phase, you understand the density and viscosity. In fact, density drastically changes with this huge temperature deviation. That is 10 degree at the free stream and 110 near the boundary layer. So at which temperature you need those values?
110 degree temperature.
60 degree.
So those who are mentioning 60 degree, that is, let's say, approximately close. In fact, that is the reasonable assumption that we can do, that it is at the film temperature or the average film temperature that I mentioned repeatedly in the last couple of classes. Okay, so at those temperatures, we will find out from the appendices or from Google whenever I give the problem, those properties, if those are missing from the problem. At that film temperature or the average film temperature, we find out these parameters from the table of an appendix or from Google or reference books. Okay, so are these information sufficient? So say I tell you this value, this combination I tell you is the new air. Okay, that is 1.896 into 10 to the power minus 5 meters square per second. K value I tell you is that it is in the order of 0.208, sorry, 0.028. Just a second. 0.028 watt per meter degree centigrade, sir. Instead of meter Kelvin, I mentioned meter degree centigrade. So what would be the next step?
Calculating the Reynolds number.
Right. So the Reynolds number in this case, how much it is coming out to be? Those whose audio is not working can type in. I have opened the chat window to see the numbers. If you can type in.
Sir, 42,000 something.
42,000. Yes.
4.2 into 10 to the power 4.
4.2 into 10 to the power 4 in this range. Yes. So the next step, Soham?
Sir, calculating Prandtl number.
Calculating Prandtl number. But for calculating Prandtl number, you have to again need the value CP, the K, and all this.
Yes.
Okay. So if those are not provided, say I give you that value as well. So Prandtl number for this case is 0.72.
Sir, what do we consider for the length in the Reynolds number equation?
Which one?
In the Reynolds number equation, what do we consider for the length?
For the length means?
Like the distance from the leading edge.
That is I didn't get it. What you are telling? Rishi, once again.
Hello?
The question is, yeah, Rishi, the question is what would be the heat transfer per unit length? So you can consider it as 1 meter.
Okay. I got it, sir.
Okay, yeah.
Yes, sir. So you have Reynolds number, you have Prandtl number. So the next step would be to use a correlation or a relation by which you can calculate the Nusselt number for this appropriate range of Prandtl number and Reynolds number. Agreed? And as I mentioned, we will try to use as much as possible that Churchill-Bernstein equation. And for sphere, we will try to use the Whittaker's proposition or the recommendation of Nusselt number for a sphere. So now I want you to use in this case, because now if you see that Reynolds number multiplied by Prandtl number is certainly greater than 0.2, you need not calculate that. It is 4 into 10 to the power 4 multiplied by 0.72. So it would satisfy this criteria. So you use the Nusselt number relation for the Churchill-Bernstein Nusselt number expression, average Nusselt number rather. And then what is the value of our Nusselt number? Okay, yeah. Now, Pooja Sharma, you got Reynolds number wrong value. I hope by now you understand what is happening.
Yes, sir. Actually, I've taken the wrong value.
Oh, okay. Achha, so Pooja, right, fine. So I need 4 of you to calculate. 4 of you means Pooja, Nidhi, Sahil, and Bhavna to calculate Nusselt number based on the table that I showed just a couple of minutes ago. That using this one of these relations, I mean whichever fits, because you have the Reynolds number range. So look at it and take that Nusselt number from this expression and calculate the Nusselt number instead of using Churchill-Bernstein, because we will see something. And let Soham, Rishi, and others to calculate based on the Churchill-Bernstein equation. Yeah, Devesh and Snehbandhu, you can use quickly the Churchill-Bernstein equation, and others use this simple correlation that is shown here. So here Reynolds number is 4 into 24, so 42,000 kind of a range. So 42,000, that means here the last expression. According to this, what is the Nusselt number? Nidhi, you were saying 34. Is this the Nusselt number based on this simple relation?
Based on chart, sir.
Based on chart?
Yes, sir.
This last correlation?
Yes, sir.
No,
Sir, it is coming out to be 127.64 from the
Yes,
chart.
Right.
Yes,
Right.
120.2.
Absolutely.
Okay.
Right. So from the chart, I'm writing the value in green color. That should come around 128, what they said. And by Churchill-Bernstein, Snehbandhu, Rishi,
127.32.
they are also 127. Are you
Sir.
sure?
Yes, sir, 127.32.
Sir, I got 195.
195. No, 195 is far off from the range. I thought that it would be, so it is typically if somebody gets in the range of 127, 128 in this range from the Churchill-Bernstein expression. So basically, the point that I'm trying to mention here, that you see here by the Churchill-Bernstein expression, what you get is closely similar, or you get an approximate value to this number by this simplified expression. So it is a few % higher
than the actual, or in fact the more accurate one. So here it would be in the range of 124, 125 by the Churchill-Bernstein expression. And here, yes. So Sanskar mentioned it's 124.09. I expected this kind of a value. So it is 124 and this is 128. So nearly 2 to 3% higher in case of this rough estimate that is given here by this table. So this is the point I tried to mention. Okay, so that means you get a close enough value to what should have been. Okay, so the next step that I got, say we go ahead with the more accurate value, which is 124. So which means H is equals to, I have K by D Nusselt number. These values are known. So H is in the range of 35 watt per meter square degree centigrade. So the rate of heat transfer from this rod or the pipe or the object, whatever you can say, per unit length, what would be? For the rate of heat transfer, what we should write? We say the Q dot, rate of heat transfer, is H. Someone prompt me.
Ts minus Ta.
H, then rate of heat transfer per unit of its length. I'm not asking flux. I'm asking rate of heat transfer. Heat flux.
2 pi r.
Sorry.
Into 2 pi r. Into
Right. That means the point is AS, the surface from which this is happening. Agreed? Multiplied by the T surface minus the free stream temperature. The H value we have calculated, 35, or say 34 point something, that value you get. The area through which this is happening is the perimeter multiplied by the length. Agreed?
Yes, sir.
That is the pi dl in this case. Pi d is 0.1 and L per unit length. Okay, so this is my A term, AS, multiplied by, I have T surface is 110 minus 10 watt. And this value comes out to be
1099.
1099.
1099 L, but we will remove L.
Watt per meter basically.
Yes, sir.
Okay, so if you want to have a total heat transfer, say 99 or 93, whatever the value that can be. So this is the watt per meter. So total rate of heat loss multiplied by the length when it is given. Any question? We quickly move on to the other problem. So the methodology that I mentioned in the last class, that anyhow we have to find out what is our average heat transfer coefficient, which means a step back, we have to find what is the average Nusselt number relation. In order to find out that relation, we have to calculate the Reynolds number, we have to check the Prandtl number, we have to see that for which range that Nusselt number should be calculated. And that range would be provided by the Reynolds number and the Prandtl number. If we use, see, this is the point that we can use Churchill-Bernstein. You can use the relations that are given here in this table. Okay, both are valid, but the more accurate one would be the Churchill-Bernstein or Whittaker's one for spherical object or anything on this point. Okay, and then once we calculate the value of h, that is the point. Once we calculate the value of h, say the Nusselt number, from there we calculate the value of h, heat transfer coefficient, convective heat transfer coefficient, and then we estimate what is the heat transfer rate or heat flux, whatever, that is the question. Any question? Fine. Okay, so we quickly move on to the next problem. So the next problem is the spherical one, as I mentioned, because we have seen the cylindrical one, and let's have it for now the spherical object. So we have a spherical object that is at a 300 degrees centigrade, 25 centimeter diameter. Okay. This is a stainless steel, so the rho is in the order of 8,000 kg per meter cube. Cp value is 480 joule per kg degree centigrade. Fine. So the scenario is that this ball was in an oven, which actually makes this whole ball temperature as 300 degree uniformly everywhere, inside it, outside it, everywhere. And then suddenly it is taken out from that oven and exposed to air. Okay, that is at 1 atmosphere. Okay, 25 degrees centigrade, and the mild air that is flowing over it is 3 meters per second at this velocity. So what happens? The surface temperature drops to 200 degrees centigrade. Okay, so you tell me that what is the average convection heat transfer coefficient during this cooling process? The value of H. And how much time it will take to cool down to this temperature. So you guys, did you do anything on the transient conduction yet? Has it been covered yet
Yes.
on the Chakraborty's part? Okay, so there you had seen such problem, right? That a ball is suddenly dropped into a pool of liquid, it quenches. I mean, isn't it?
Yes, sir.
So we will not go into that transient scenario. Okay, but that is, I would say, the more accurate process to do this, because this is a transient process. But here we would like to have an estimate by the knowledge of convection, because there you have heard the term called the lumped parameter analysis or lumped parameter calculations and all this stuff. We will not go into that detail. We consider it in a more simplified manner. So there are several assumptions we will do here. One is that the radiation is again neglected or negligible. Fine. The outer surface temperature of the ball is always, say, at a constant temperature. Or say, not constant, I would say it's an uniform everywhere at all time. Okay, which is not, say, practically correct, or it's not pragmatic. But the assumption we consider that the outer surface temperature of this ball, because it is a dynamic process. Okay, so it is not that everywhere it would be 200 at the same time. But we consider for the sake of simplicity. And also remember one thing, that once this is a quite transient process, that means time dependent process. So once the air comes or wraps around this part and it starts to cool, as it cools, as the temperature difference changes, the heat transfer coefficient also changes, isn't it? So we will neglect that aspect as well. So what we will assume is that the surface temperature of the ball is constant, okay, for the sake of simplicity and for the sake of calculation, and that is again at say this is 300 plus 200 by 2, which is 250 degrees centigrade during the entire process. So as to calculate the heat transfer coefficient, the average heat transfer coefficient, which is consistent. Again, this is not real, or this is not true, but we still will have an estimate that how much time it may take to cool down. So the values that are necessary is that the K value of this air is say 0.0255 watt per meter centigrade. Nu is 1.562 into 10 to the power minus 5 meters square per second. Mu is 1.85 into 10 to the power minus 5 kg per meter second. And Prandtl number is 0.73. This is all at the atmospheric temperature, which is 25 degrees centigrade. And at the same time, I also mention that this dynamic viscosity of air at 250 degrees centigrade is 2.76 into 10 to the power minus 5 kg per meter second. So these are the properties of air at free stream temperature. This is at the surface temperature. So what we would use and how do we use that, this information? The purpose is very clear, right? When I give all these details, that immediately tells you that look at that expression that Whittaker proposed, because there you had these terms, that mu by mu s. That is the mu, if I say this one as the mu infinity, so the mu free stream by mu s. So which means the similar step we follow for this problem, that we calculate Reynolds number at first for this problem. And what would be the Reynolds number in this case? Has somebody calculated already?
But so while calculating the Reynolds number, the new value, it should be like at 300 plus 25 divided by 2.
The new, no, I mean, in that case, if you remember the Whittaker's propositions, when we mentioned it is everything at the free stream temperature. Okay, all the properties that we calculate are at free stream temperature except the correction factor, that is the mu s, which is the mu surface. Here, this is the relation.
So here
Except this-
everything is at like surface free stream.
Free stream, right.
Okay.
So what is the Reynolds number that you have calculated?
48,000.
48,000. So in the order of 48,000, numerically close to 4, like the previous one, 4.2 into 10 to the power 4. Here it is 4.8 into 10 to the power 4. So which means, if I go back to this expression, you remember here the Prandtl number, the Reynolds number range was maximum of 80,000, which is falls in between this range. Okay, the Prandtl number here is already in the range. It is mentioned as 0.73. So which means we can use this expression in order to find out what is my average heat transfer coefficient. So you use this Whittaker's proposition to find out the Nusselt number. And the Nusselt number would be in the range of
Sir, is it 135?
in the range of 130 to 135. So which means the value of H is
13.787.
13.787, which is near about 0.8. 13.8, what would be the unit? Shubhajit, what would be the unit? Heat transfer coefficient?
Sir, watt per meter square Celsius.
No, watt per meter square. Watt per meter square? Yes. Watt per, yeah. Yes. So this is our answer for the first part, that what would be its heat transfer coefficient. This is based on the assumption that the outer surface temperature of this ball will be uniform at every time or at all times. Now we have to estimate how much time it will take in order to come down from 300 to 200, or say in order to come down to this whole ambient temperature at a steady state scenario. That would, okay. So at first let's calculate what would be the time it takes to cool down from this 300 degree, if that is considered at T is equals to 0, once you take out from the oven, and immediately it cools to, not immediately, it will take some time that the surface temperature will come at 200 degrees centigrade. What is that time? That the temperature decreases from 300 degrees centigrade to 200 degrees centigrade of this ball. How do we do that?
So you
What
can
is the
find out the Q dot,
right?
the
Which is the
average Q
average,
dot.
right? Absolutely. Which means the Q dot average based on this average. Which would be how much? So H, again in this case, we have HA delta T. The value A would be, what is the value of A?
Sir, 4 pi r square.
4 pi r square.
4 pi r square, absolutely. So then you can calculate what would be the Q average, Q dot average rather. What is del T here? What is the value of del T? Realize the scenario that a ball came out from an oven that was uniformly at 300 degrees centigrade. Now the question is that when the temperature of this ball would be 200 degrees centigrade.
Del T will be 250 minus T stream.
T
Yes, sir.
right. Because see here this is not the simply, I mean, this is what we are assuming is a very simplified situation. It is not possible for the ball to be of 200 degrees centigrade at a particular time, because the inside temperature of the ball may be higher than the 200 degrees centigrade. In fact, it will be higher. At the center of the ball, the temperature would be higher than 200 degrees centigrade. So the heat transfer coefficient, okay, and this time is not what is constant value, that when the whole ball would be at 200 degrees centigrade. But we are assuming it that the ball will come from 300 to 200 degree as a whole or a lumped value. Okay, this is how the simplification is happening in this calculation. So in this case, what is the Q average or Q dot average? Heat transfer coefficient, heat transfer rate, the average value. At least the magnitude, if not the accurate answer. It is HA delta T. You know H, you know A, you know del T. So what is the heat transfer rate? Devesh, what would be the unit of heat transfer rate?
Sir, watts.
Watt.
Watts.
So yeah. So how much? Watt.
609.36.
609.36. Okay, so we consider, say, in the magnitude of 609 watt. Okay, so this is the heat transfer or average heat transfer rate. Now, how much heat transfer is happening? This is what means joule per second. How much heat is being transferred? That means how much J joule of heat is being transferred. If you calculate that and you divide it by this value, by this rate, you would have an estimate of time. So how much heat is being transferred? How do we calculate that?
So we have the row, we have the volume. So from
Right.
that we'll get the mass of the spherical substance. We also
Yeah.
have its Cp, and we'll multiply it by T. So it will be mCp/dt. So we have everything.
Absolutely. So that means Q is basically mCp delta T, where m is basically we have 43 pi r square r cube. Okay, or say this rho multiplied by pi d cube by 6. Sorry. Okay, so this is m, the Cp value is given, and delta T here is 300 to 200. This is the value that is coming down, or this is the temperature that we need to be dropped. If you quickly calculate, you'd find the mass of this particle, means this ball. It basically the value that we have given here, 8055 rho multiplied by the volume, pi d cube by 6. Which would be around, Namaskar, how much? The mass of the ball?
Approximately 66 kg.
Hello, sir.
Yeah.
Yes, sir. My mic was not working.
Sorry.
Sir, my mic was not working.
Okay, fine. No, fine. So 66 kg. You should be able to calculate this as quickly. Okay. So m is 66. Cp value we have mentioned here. Yeah, 480. That is mentioned, and the temperature drop, that is 100 degrees centigrade. So basically 66 multiplied by 480 multiplied by 100. This much of heat we have to take it from the ball at the rate 609 watt. So our del T, or del T means the temperature, the time it takes is basically this 66 480 multiplied by 100 divided by 609 second, because watt is joule per second. This will give you a value in seconds. Now this is a approximate value of time that it would take. It is not obviously the accurate one, because there are several assumptions we have made, which is not pragmatic. But as I mentioned earlier, we being the engineers, we quickly need some numbers to work with, or to estimate something, or to guess that what is the magnitude of this problem. Okay, so this would give us this kind of a reasonable estimate with which we can work further. So what is this value? Can someone tell me?
Sir, around 5,000 seconds.
5,000 seconds means we have so something between 1 hour to 2 hours. It is not. It is more than 1 hour and below 2 hours. Isn't it?
Yes, sir.
So 3600 seconds and 7200 seconds in between these two, so which is between 1 and 2 hours. So this would be your, say, next step of calculation if something has to be designed or something has to be taken care of, that it is not going to take 2 hours, but it would certainly take more than 1 hour to come down to this kind of temperature. But the point that we have seen in this lecture, again, we are lagging with that objective of studying this bank of tube, but that's fine. We have seen the application of these relations that we have calculated or that we have seen. So on the first case and the second case, in both the cases, approach, again, let me repeat it for the final time in this class, is that approach is same. We find out what is the Reynolds number, we check what is the Prandtl number, then we look the proper relation or appropriate relation for of Nusselt number, for which we can, in this range of Reynolds and Prandtl number, we can take that relation. We calculate the average Nusselt number value. From that average value, we take the average heat transfer coefficient. And then the subsequent step or the other corollary work has to be done. Any question? Because, yeah, we have crossed the time. Yeah. Any question? Okay, then. Thank you. So,